Yeah, my name is Peter Funk. It's my pleasure today to introduce today's event, Tomas Olsson's dissertation. And I would also like to thank Amy Lutfi, who is the opponent today and has been putting lots of work into preparing, and so that's a quite responsible job. So I'm glad you accepted it and is doing it. We also have a grading committee and Henrik Bogström from Stockholm University. And we have Niklas Lavesson from Blekinge Institute of Technology. And we have Maria Lindén from Mälardalen University, professor here. So we have a very honorable grading committee with 3 professors. So thank you very much to accept it. And of course also the supervisors, Anders Holst, Marcus Bengtsson, Ning Chong, and Peter, oh sorry, yeah, I didn't see you sitting out there, and myself then. So I will tell you a little bit of the procedure. First, Tomas will present his work, and that will be about 30 to 45 minutes. I think you will use up your 45 minutes, and then I will stop it if it takes longer. And after that, the opponent will have a discussion or questions and discussion with Tomas about his research the last 4 or 5 years, and look into that one. And after that, the grading committee will also add on some questions. The opponent maybe will use 20 minutes or 30 minutes, or if you are not happy, you can spend 2 hours. There's no limit on the time, so it's completely open here at Mälardalen University. Then the grading committee will ask some questions. Maybe they have something to ask to complete from their own perspective. And after that, the audience can also ask Tomas some questions. And after that, the grading committee will go away and make their decision. And then the rest of the audience can go then to the Java, to our coffee room, and we'll wait there, and there will also be a little bit snacks and crisps, and and wait for the grading committee to come and announce the result. Yeah.
Let's do a short break to let Jonas out after Tomas' presentation, like a minute or 2.
Yeah. Okay. Yeah. We can even have a very short, after Tomas' presentation, we can have a short 5-minute break. Yeah. Please, the floor is yours.
First, I want to thank you all for coming here today. And so my name is Tomas Olsson, and I will present my PhD work here, a data-driven approach to remote fault diagnosis of heavy-duty machines. And as you can see here, there is almost everybody involved in my work during this. So I'm have been working at NDH and 6 Swedish ICT during this time. In close cooperation with Volvo Construction Equipment. So my title of the thesis consists of mainly three big concepts: data-driven approach, remote fault diagnosis, and heavy-duty machines. So I will start to give you some background on this. What does it mean? So heavy-duty machines. This is the kind of machines I have been looking at. Mainly wheel loaders have been the kind of main, the first biggest picture here has been the main focus in this thesis. But we've also been looking at trucks and container cranes. So why does this matter then, my research on fault diagnosis? Well, first of all, operators of machines, they are very interested in having their uptime, that the machines are available when they plan to use it. They don't want to have no unplanned stops because of that the machine fails. So we could monitor the machines and automatically discover then something is wrong, we could foresee that the machine will fail. And we can take measures beforehand and plan a stop for fixing this. As well, there is, if you can guarantee the availability of the machines, you can start, not as a manufacturer, you can start selling more complex products, like the service of having a wheel loader working for you. So you can sell the availability of the machine instead of the machine itself. So this opens up for a lot of good things. And why is it a problem then? Well, the complexity of machines, these machines, for instance, wheel loaders used to be mainly a mechanical system, but more and more electronic equipment is put on these machines to make it better. And so does the complexity of the machines. They get more advanced and they get harder and harder to locate faults and diagnose the faults. And then it takes a longer time to repair the machine than when they break. And so it would be nice if we could do this automatically. Since we already have electronic systems on board the machine, we can use them also to monitor the machine. And but these machines, you can't put a lot of computational resources on board the machine, and you can't. And often the communication from the machine to some off-board service is very limited. Like wheel loaders can be used in mines, in remote places, like deep into the Amazonas or something, where they have a very expensive communication off-board the machine. So we have to take that in consideration when we are monitoring these machines. And then if we start to monitor all the signals, all the sensors on board the machine, we can, for instance, you can monitor anything on this machine, like the speed of the wheels and the pressure, the temperature, everything. It will be generated very fast. It will generate large volume of data. So it's not, and since you have limited computational resources on board the machine, you have to have a trade-off between what you can do on the machine and the limited communication. Make it a trade-off to do what can you send from the machine to process remotely. So, having this in considerations, what we want to do, we want to answer basically three questions. How can we detect faults? And what kind of faults have we detected? And thereby know what to do to repair the fault. And can we trust the diagnosis? If we get it wrong, a bad faulty class type of fault, we will make a wrong repair. And the two first questions we in this thesis consider under the term fault diagnosis, fault detection and fault classification. So we look at the system as a whole. We actually probably have more than one machine we can monitor. So we have a fleet of machines. And the idea in this thesis is then that we do some part of the processing on the machine, like fault detection, to detect what is wrong with the machine. And then we can send a detected fault off-board for further processing to determine what type of fault do we have here. And then we could, in theory, make more, use more data available than on board the single machine for doing this. Okay, so the last thing in my title of the thesis is the data-driven approach. So data-driven methods are methods that can learn from experience and improve its performance. So the kind of purpose is to generalize from seen examples to unseen examples. You will probably not have exactly the same data, the sensors and the signals from the machine will not be completely identical to what you have already observed. So you have to kind of make an abstraction to generalize. So, well, examples of what we want to do is like classification, that you want to this is a basic kind of basic definition that you want to distinguish between different types of things, faults in our case, but you could, for instance, for images, you can classify images into cat, dog, fish. And you can do regression where you want to estimate a real value. Or you can do clustering when you have to automatically learn groups of data belonging together. Yeah. And yeah, I will skip this and go for the, okay, we look back to this kind of setup, but I have this distributed processing of machine, fault detection, fault classifications. Then if we look at how the data is generated, we have actually continuous streams of data, foremost on board the machines that we want to manage on board the machine. And we only want to let a minor, less, not as much data go to the centralized server for further processing. So you have a stream of data that is continuously generated, and you have to filter out what you want to look at the machines and send it off-board to further processing. Okay, so in this is I propose this system, this framework architecture for doing this job. We have onboard diagnosis and off-board diagnosis part. So to the left we have some signals from the machine. They could be belonging to a certain event like a gear switch or something. And we want to then extract some features from those signals. The features what we are interested to look at in the diagnosis part. And the next part is to have an anomaly detection that looks at the data to see if something is abnormal or looks faulty on the event level. And this then will result in this is continuously checking if the gear switches are okay or not. And each time it's not okay, it sends this off-board. And the next in number 3 there, we have a stream anomaly detection that will look at not the individual events, but the events as a group, like a sliding window approach. And say, oh yeah, it's not, because the local anomaly detector will probably not be perfect. It will probably have some random noise, sending out faults when indication of faults when there are no one. So the stream anomaly detection will take care of that by looking at all more data points. Yeah, and the last point is fault diagnosis. I put here, and that is mainly fault classification. So if we look at the questions where they belong, the question we want to answer. So the anomaly detectors are for detecting the faults, and the fault diagnosis component here is to find out which fault it is, and then also to assess if you can trust this diagnosis, this classification. So we have to start with the 2 anomaly detection components. And for you who doesn't know what anomaly detection is, this is the informal definition I use. An anomaly is a pattern that deviates substantially from what is considered normal. And there is some assumption that we usually have a lot of data that we can consider as normal data. That is nothing wrong with this data. It's just how the machine behaves, how it's expected. It's more common with normal data than anomalous data that are not as we want the machine to work. And then we want to be able to classify cases, the data, into being normal or anomalous. Okay. And that can be done in different ways. We look at the first one, the onboard anomaly detector. In this is I trained a classifier. I assumed that we had a small amount of anomalous data, faults, that I could use to train a logistic regression to distinguish between normal and anomalous data. And then I also, as input, I had proposed to use a statistical clustering Gaussian mixture model that fitted on each feature value independently of each other. The idea was to capture some generality about anomalous data. Then we assumed that all the training of the classifier was done off-board the machine, while the classifier was used on-board the machine. So we could use more data for the training in the off-board server, so to speak. And we evaluated this. One is strange. Something has happened to this slide. I don't know what it can be. Anyway, this would tell us which. Very strange, actually. Okay. Anyway, I will tell you. Anyway, we simulated oil leakage on a wheel loader. And then we collected 6 different signals from the machine, differentials. We only looked at gear switch 1 to 2. So we switched from gear 1 to gear 2. And we looked at the 6 signals that were generated during that gear switch. And it was the differential speed 1 and 2. That means when the gear is moving from one what is it called now? Differential speed, you have this, now it's lost. Anyway, it moves from gear 1 to gear 2, and you have a speed that shifts from one gear to the other one. And then we looked at the in and outgoing speed from the transmission, the gearbox, and also the turbine torque and turbine speed we looked at. And we extracted some features. We got 337 cases, among them were 63 was faulty cases. We only had one single fault, that is oil leakage. But we had different severity levels, 1 to 7, depending on how large the oil leakage was. And the simulation was done on the vehicle using a valve that we could open. And we compared the performance of this anomaly detector using 3 or 5 features extracted from those signals, and this is the result then. And the first, let's see, original features there. Then we used only the features that we extracted, and then we compared it using with the area under the curve that tells us how good the anomaly detector is to distinguish between anomalous and normal data. And 0.5 means it's only random noise. I mean, it doesn't have a clue on what means. But if you're close to 1, you have quite a good performance. And we have quite good performance on all these different setups. But the original features, we have the best area under the curve for using all 5 features, not very strange. But then we had this statistical process, and we fitted the Gaussian mixture module. It didn't affect the result that much. It seems that all of them are pretty equal in since we have quite few examples, cases that we trained and tested on, we can't say much about the significance between the different setups. But we can say that we are able to distinguish between normal and anomalous cases. Okay. Let's go on to the stream anomaly detector that is used to monitor not individual cases, but groups of cases. This is a quite general approach. The only assumes that you have cases are divided into groups. So you have a set of groups you want to check, and each case has an anomalous score, telling how anomalous it is. It can be 0, 1, binary anomalous score, or a continuous value. 0 is non-anomalous and greater values are how anomalous it is. Okay, and output will be a probabilistic anomalous score. That means we use probability theory to assess the anomalousness of the groups of cases, not the individuals. This makes sure that we can filter out random noise. So if we get individual cases that have a high score, but they are just one of them in one group, it's not that significant. So we call this probabilistic anomaly aggregation, and it's an unsupervised approach. We have no mathematical statistical model of the data points directly, but we use an empirical distribution of the anomaly scores for this. So we look back to the definition of anomaly detection. So we have to consider what is normal. What do we consider normal? We have to decide, also answer the question, what is deviation? What is the deviation? And what does it mean to be have a substantial deviation? Okay, if you look at the first anomaly detector we have looked at, it's just look at point anomalies, the individual anomalies from the different cases. So it's used to distinguish between single points with a normal, like this, just knowing which the logistic regression will just fit the line that will separate the normal from abnormal. But now we are looking at cases as a group, a collective. We want to be able to say if these two groups, which one is an anomaly compared to so we make this assumption of normal groups. They contain few point anomalies. Okay, since I think it's reasonable. And then the deviation from the normal is the probability of observing equally many or more point anomalies by chance alone. And then we can set, since we have this probability, we can set a significance level what to consider as anomalous. And we use 1 per 1 million, 10 to the power of -6 as a probability. If it's lower than this, we consider it as an anomaly. So how do we do that now? So if we look at the empirical distribution, this is an example from a real. This is container cranes movements, the time delay. We consider in this case we had a model of how long time it should take to move a crane from one position to the other. And then we computed the difference between the actual time and the expected time. So that is our anomaly score, the delay. And then we can, if we look at the top 1% of the scores, anomaly scores, the probability to fall into one of the red, I don't know if that's exactly 1%, it's just to visualize this. Then the probability of any score being, if the anomaly scores were completely random, generated by random, the probability of falling into the red part is 1%. If this is only by pure chance that we, and if we look at the top 10% of the scores, its probability is 0.1. Okay. So, if we know the number of cases, data points we have, a number of anomaly scores we have, then we can say that the probability of observing observing Y anomalies by chance alone in a group of n points is the binomial distribution. So, and then we say that the probability of observing equally many or more than Y anomalies is the expression down here, shown there. This is just the sum over all the beta binomial computation in the above expression. And so the lower part will be our anomaly score if we take the logarithm of it and the negative logarithm, and we get the anomaly score we basically use, but it's easier to think in probabilities when you're talking about it. So, but we didn't just have, we could use a binary anomaly score. So then the ones would be the Y, all the anomalous scores were 1, but we have actually could use a continuous value for the anomalous score. So to solve this, we just partitioned the anomaly scores into a set of predefined fractions. So we look at a set of fractions that we think will cover the parts that we are interested in. And then we scan through all the fractions and see if any of them are below this anomaly threshold, 10 to the power minus 6. Then we can see if the group is anomalous, it is enough that any of the partitions are anomalous. So then we could, if we want to rank the groups, we could rank it by the number of detection times, the number of instances it has been detected as anomalous, given the partitions of fractions, or we could use the maximum on the negative log probability of the expression above there. So, okay, we have applied this. We didn't have, if you look at it as, if you have many groups of data, we have evaluated on artificial data where we randomly generated some groups of data, considering normal data points Gaussian distributed with a mean of 0. And then we had anomalous data points that were also not Gaussian distributed, but with another mean value, and there were fewer of them. And then we tried to detect the anomalous groups of data points using a Gaussian statistical model. So we set the Gaussian model of the mean of the groups of data that we have randomly created. And then here now I should have something to point with. But anyway, where it says prec is precision, that means the percentage of the detections that are correct. That is, if the algorithm says that they have detected something abnormal, and it actually was abnormal. And the number of those that are actually correct. We see that this simple Gaussian baseline will, and the 1, 2, 3, 4, the standard deviation above there is that we change the standard deviation of the normal data points. So we increase the standard deviation. Started from standard deviation 1, and we create artificial data for that. And then we create anomalous data with another mean value. And as we increases the standard deviation of the normal data, great. As we increases the standard deviation of the normal data points, we see that the precision starts to decrease here. And the second one is the false discovery rate. That means pretty much 100 minus the precision here. It increases here then. And the recall, that is, of all anomalous groups, how large fraction did the algorithm detect? And here 83% of all the anomalous groups, and then it slowly decreases, or maybe fast, you would say. Okay, we will leave the last column to later. Now, this is the probabilistic anomaly aggregator that we implemented. First of all, precision, you have 100% all over here, regardless of the standard deviation. And the false discovery rate is, of course, 0 all the time. That is due to they have this high significance level of 10 to the power minus 6. But the recall is quite high, 100% there. And then it slowly decreases, much lower than the Gaussian model. But here at 5, you see that this is much lower than, this is 26 and this is 16, but we don't have any false discoveries, no false positives. And then here also we have much lower recall, but we don't have any false discovery rate. And the last comment is interesting because I changed the definition of what is normal here. Now I changed and started to, instead of having the mean, I changed to letting the mean. I stopped varying only the standard deviation here, but I started to vary the mean, and suddenly this normal distribution failed, but the proposed approach are really still very successful. 100% precision and 88% recall. So it was just illustrating that our algorithm was more flexible to detecting different types of anomalies. Okay, so we also evaluated it for data streams. This was the first was like a batch. We had many different groups, but in this case we only have a large window of. We have this data stream of fault anomalies from the local anomaly detector, and then we have a most recent window with the latest anomaly scores, and then a large window with a larger history of the data. And then we compared using, we only looked at the deviation of the anomalousness of the most recent group. So the most recent window is a group, and it compares to all the other data. So only one group in this case. And we didn't have streaming data actually, so I simulated this to be able to evaluate this in this case. So I used 3 different public data sets. And the steel plate is faults from some steel plate production. Landsat is some satellite data. I think it was for classification of land, I guess, how they are used. And shuttle data is when they send out space shuttles, whatever it's called. Anyway, doesn't matter. I simulated streams of data by picking a small subset as used for training, and then I used the remaining to sample from, to randomly pick samples. And I used some of the data as normal data points and some of the data as faults. So I started out sampling only normal data points. And then in the middle, I changed and started to, for 50% of the time, I sampled from the faulty cases. And then the algorithm should detect that change in the data stream. And as you can see, this is the precision. For steel plate, we have 100%, and for shuttle data, almost have 100%. We almost detected all the detected anomalies or faults were actually faults. While the recall was lower here, only 70%. That means we missed like 30% of the faults here and here. But the shuttle data, we had almost 100% recalls. We detected all the faults. And for steel plate case, it's because we had much less data. So the local local anomaly detector hadn't that good detection rate for the individual individual cases. And the Landsat data, there was one class that the local anomaly detector were not able at all to detect, even if it was trained for it. And then we could look at mean delay. That means how many simulated time steps did pass before from the time when we put in the new fault. And you can see for the steel plate, 190 data time steps were the delay from when the fault was injected. And it's quite high, but it was much lower here, and that is reflected in the recall and precision. Okay, so it was quite successful for the simulated data at least. Okay, now we looked at the question of what kind of fault is it? And here we had the individual classification and stream classification, similar to the fault anomaly detection. And for classifying the individual anomalies, we use the case-based reasoning approach. Case-based reasoning is like the assumption is that similar problems have similar solutions. And if we have a new problem here, we retrieve a set of old cases similar to the new problem. And then we can reuse the old cases to solve the new solution, or, for instance, predict the new class using the old cases. And then we store the new case. If it's good, we store it in the case base. So for this approach, we use a similarity. This is what we use for all CBR, case-based reasoning approaches we use. We have used the weighted Manhattan distance because it was the best one. In many cases, we normalize the features using standard deviation. And for weights, we use the maximum information coefficient as weights. It's a measure of information, mutual information between the target concept and the attributes or in features that is in the cases. So it's higher information make it higher weight on that feature. And for prediction, in case of classification, we use majority voting. That means we count, if we retrieve the K or number of most similar cases from the case base, we count the number of cases with a certain class, and then with most votes wins, so to speak. And regression, we just use the mean value of the retrieved cases. Okay. When we look at the stream diagnosis algorithm, that means the stream classification algorithm, it starts by to identify the anomalous cases on board the machine. Okay, we have already talked about that. Then we identify the anomalous window of most recent cases. That's what we use the stream anomaly detector for. And then and this could actually be done on board the machine as well, if we have the computational resources to store the windows of cases. But now we classify each case individually using the CBR classifier. And then we aggregate the anomalous cases, the classification of the individual anomalous cases into a single prediction. That means pretty much actually similar to what we do with the CBR approach. Because we tried 3 different approaches. Simple majority vote. That means we just count the number of anomalous cases classified with a certain class. The class with the most classifications wins. And then we have the weighted majority vote, where we have a weight for each case, like the fraction, the confidence given by the CBR classifier as a fraction of instances with retrieved instances with the same class. And then we have a third aggregation approach. That's the Dempster-Schaeffer fusion approach. That is, it's whole theory of itself, how to combine different independent sources, the weights from different independent sources into a unified prediction. I'm not going into that in detail. It's in my paper in the thesis. Okay, but we evaluated it on the same data set that we used for the stream anomaly detector. And what to say is that, well, they are quite similar in performance. The weighted majority vote is a little bit better than the Dempster-Schaeffer for one of the data sets. They are equal for the other ones. But we compare, the baseline that we compare with is if we just had one single individual case for doing classification. And the last detected case that we have detected on board the machine, that is, it ignore all the other cases that we have in this most recent time window, and use that as our classifier. We only have 65% here and 87 and 97% correct classifications. So it's at least on this simulated data it is better. Yeah, it assumes that your individual classifier is not always classifying correctly. If it always was classifying correctly, of course it would be wouldn't improve the final classification then. Maybe it. Okay. So the last question was, can we trust the diagnosis then? And the goal is to support a non-expert user in assessing the reliability of a prediction using case-based reasoning in this case. And why? Well, we want to have users accept the system. If they know how to understand, if they can rely on the predictions that we produce, then of course they will use it. And it probably can help making better decisions as well. And this is an area called case-based explanation, where we use preceding cases to explain. And you could argue it's a more intuitive approach. I don't know if it can be proved that it is. But in some areas, like in the medical area, they use analogy and a lot of reasoning comparing with previous cases. So it can work very well. So the idea is to query a CBR system for relevant preceding cases and then deliver an explaining summary. And in our case, we apply this for probabilistic methods. So you assume they have a probability model, a probability distribution that you can look at. And we want to connect what are the preceding relevant cases when you have a probability model. And as explaining summary, we will use the local accuracy. So the reliability of probabilistic diagnosis, we have come up with similarity metric that measures the similarity, or we use a statistical similarity metric that measures the information that cases have similar information with respect to the probability distribution. So in essence, it will be a comparison between the probability distributions and features, and mathematically you will get a transformation of the original features into probability distributions over fault classes in case of fault classification. And and then the reliability prediction is the fraction of the most similar previous cases that are correctly classified. So instead of having predicting a class, which we use the preceding cases, how good was the algorithm is in predicting for other cases, and see for similar cases what is the probability that they would be correct now for a new case. So example, what can we do? If we have this classification, this is a fault case that we want to classify. And this, we trained the logistic regression classifier to classify the faults from this plate, steel plate faults that we used before. And it gives a very high probability for the prediction, 73%, or quite high at least. But the local accuracy, the CBR approach says it's only 10% correct. That means 1 of 10 previous cases that it has predicted, similar cases, it was only 1 of them were correct. So if we look here, we have predicted class here is 7, and this is a target case. And we can see the true class here but we don't know that, and then we use this in reality, but we use it in illustration. This is the 5 most similar cases here. And it's predicted 7 for all of them, but none of them were correct. But still, it has quite high probabilities for us. So that's the idea. We can use the preceding cases and a summary of the performance of the algorithm for the previous cases to assess the performance for a new case. So, that's actually all the research I have covered in my thesis, almost, I think. So, in summary, we have, for how to detect faults, we have 2 research contributions. We have the statistical approach on board for detecting individual faults, and we have the group anomaly detection to detect groups of faults that you could use on board and off board the machine. And then, in terms of what kind of fault it is, we have also 2 research contributions. We have the fault classification of the individual cases using the CBR approach in combination with statistical feature processing with the Gaussian mixture models. And then we have the fault classification using aggregation of individual cases from a stream of cases. And last, we have the research contribution for the question if can we trust the diagnosis with this case-based reasoning approach for reliability prediction. So that's pretty much summarize the contributions of my thesis. And as for future work, as you told you, we actually just had one single real fault from the machine, wheel loader machines. And we should really need to investigate more for more faults, maybe from other components on the machine. This time we only looked at transmissions. And I would really like to look at real data streams, not it. Right now we have just looked at simulated. And of course this is meant to work on a fleet of machines. We have really just looked at a single machine. And we also assume that we already know most of the classes that we're looking at. We should work on novelty detection to take new types of faults that we haven't learned on before. And actually, we also would like to be able to perform some of the fault classification on board the machine and just leave the very hard cases to the off-board processing. So, yeah. And then we would work more on the onboard, off-board learning. What should be learned onboard the machine and what should be learned off-board the machine. And then the reliability approach for assessing the reliability of a prediction should be integrated with the stream classification. We actually get weights that can be interpreted as probabilities when they do this aggregation of the individual classifications. And then last thing is the PROG, the probabilistic anomaly aggregator. We should investigate it for more generic and compare it to other change detection algorithms that are used today. I think it has quite a potential there that I didn't have time to do in my thesis. So, okay, thanks. That's what's all for me. Thank you for your attention.
Thank you. Yeah, then we have a 5 minutes break, and then we